As another example, we find the interval in which the function f of x is equal to sine of log x minus cos of log x is strictly increasing. Here log x is the natural logarithmic function because its base is given as e, and we know that the natural domain of the natural logarithmic function is open interval 0 infinity. The graph of the log x is shown in the figure. By looking into the figure, you can also see that open interval 0 infinity is the natural domain, and the image of logarithmic function is the entire real line. Also, we know that the natural domain of the trigonometric functions sin x and cos x is the same, and it is hence the natural domain of the given function f of x is open interval 0 infinity. That is, f of x is well defined only when x greater than 0. Now differentiating with respect to x, we find that d by dx of sine of log x is equal to d by du of sin u times du by dx, where we take u is equal to log x and applying the chain rule. Now d by du of sin u is cos u, so this is equal to cos u times 1 by x, because du by dx is equal to 1 by x, because here u is log x. So we get d by dx of sin of log x is equal to cos of log x by x. Similarly, we can find that d by dx of cos of log x is equal to negative sin of log x by x. Thus, f prime of x is equal to cos of log x plus sin of log x all divided by x. Now we note that sin pi by 4 is equal to 1 by root 2 and cos pi by 4 is equal to 1 by root 2. We introduce sin pi by 4 and cos pi by 4 in the summand in the numerator, and in order to compensate that sin pi by 4 and cos pi by 4, we multiply with the root 2, because sin pi by 4 and cos pi by 4 is 1 by root 2. Now we use the trigonometric identity that sin a cos b plus cos a sin b is equal to sin of a plus b, and we get f prime of x is equal to root 2 sin of pi by 4 plus log x all divided by x. Now by the results we have seen in the previous session, we know that the function f of x strictly increases when f prime of x greater than 0. The figure shows the graph of the trigonometric function sin x. By looking into the figure, we can see that sin x strictly greater than 0 when the value of x is between negative 2 pi to negative pi, when x value between 0 to pi, x value between 2 pi and 3 pi, and so on. That is, sin x is strictly greater than 0 when x lies in the open interval where its left end point is an even multiple of pi and the right end is the immediate successor, which is a odd multiple of pi. So we can write like this: sin x greater than 0 if and only if 2n pi less than x less than 2n plus 1 pi for some integer n. Now sin of pi by 4 plus log x strictly greater than 0 if and only if 2n pi less than pi by 4 plus log x less than 2n plus 1 pi for any integer n. Why this situation? We have the observation just now that sin x strictly greater than 0 when x lies between an even multiple of pi and an immediate odd multiple of pi. So this is possible if and only if 2n pi minus pi by 4 less than log x less than 2n pi plus pi minus pi by 4 for any integer n. And this is if and only if e to the power 2n pi minus pi by 4 less than x less than e raised to 2n pi plus 3 pi by 4 for any integer n. How can we write like this? Because we know that the exponential function is a strictly increasing function, so that 2n pi minus pi by 4 less than log x if and only if e to the power 2n pi minus pi by 4 less than e to the power log x. What is e to the power log x? E to the power log x is x. Similarly, the other one can be obtained. So we conclude that f of x is strictly increasing when x lies in the open interval e to the power 2n pi minus pi by 4 comma e raised to 2n pi plus 3 pi by 4 for any integer n. Now we examine the situation when x is equal to e raised to 2n pi minus pi by 4 or x is equal to e raised to 2n pi plus 3 pi by 4. Putting x is equal to e raised to 2n pi minus pi by 4, x is equal to e raised to 2n pi plus 3 pi by 4 in f prime of x is equal to root 2 sine of pi by 4 plus log x all divided by x, we get f prime of x is equal to root 2 sine 2n pi by x or f prime of x is equal to root 2 sine of 2n plus 1 pi by x. And both has the value 0. Thus, f of x is strictly increasing when x lies in the closed interval e raised to 2n pi minus pi by 4 comma e raised to 2n pi plus 3 pi by 4 for any integer n. As another example, we show that x by 1 plus x less than log of 1 plus x less than x for all x greater than 0. We first prove the first inequality. For this, we let f of x is equal to log of 1 plus x minus x by 1 plus x, where x is taken as greater than or equal to 0. Now we differentiate f of x so that f prime of x is equal to 1 by 1 plus x, because the derivative of log of 1 plus x is 1 by 1 plus x. Now the derivative of x by 1 plus x is obtained using quotient rule of differentiation, which gives 1 plus x times derivative of x minus x into derivative of 1 plus x all divided by 1 plus x whole square. So this simplifies to 1 by 1 plus x whole square. So f prime of x is 1 by 1 plus x minus 1 by 1 plus x whole square. So this simplifies to x by 1 plus x whole square. Now looking here, we can see that the denominator is always a positive number, and whether f prime of x greater than 0 or f prime of x equal to 0 depends on the value of x. We can see that when x greater than 0, f prime of x greater than 0, and when x is equal to 0, f prime of x equal to 0. This shows that f is strictly increasing in the left closed right open interval 0 infinity. Also, f of 0 is equal to log of 1 plus 0 minus 0, which is equal to log 1, which is equal to 0. Okay, so f of 0 is equal to 0, and we have f is strictly increasing in left closed 0 infinity. So if we take a number x greater than 0, by the strictly increasing behavior, we have f of x strictly greater than f of 0. What is f of 0? F of 0 is 0, so that f of x strictly greater than 0. What is f of x? Log of 1 plus x minus x by 1 plus x. This value greater than 0. So we have log of 1 plus x strictly greater than x by 1 plus x for all x greater than 0. To prove the second inequality, log of 1 plus x less than x for all x greater than 0, we let capital F of x is equal to x minus log of 1 plus x for x greater than or equal to 0. Then we differentiate capital F of x and get f prime of x is equal to 1 minus 1 by 1 plus x, which on simplification gives x by 1 plus x. From this it follows that f prime of x strictly greater than 0 for all x greater than 0 and is 0 when x is equal to 0. So that f is strictly increasing in the left closed right open interval 0 infinity. We note that f of 0 is equal to 0 minus log of 1 plus 0, which is equal to negative log 1, which is equal to 0. And since capital F is strictly increasing in the left closed right open interval 0 infinity, for any x greater than 0, f of x strictly greater than f of 0. What is f of 0? F of 0 is 0 already obtained. So we have x minus log of 1 plus x strictly greater than 0 or x greater than log of 1 plus x for all x greater than 0. Combining 1 and 2 we obtain as desired. As another example, we show that x minus x square by 2 less than log of 1 plus x less than x minus x square by 2 times 1 plus x wholes for x greater than 0. To prove the first inequality, we let f of x is the difference of the first two functions, and that is equal to log of 1 plus x minus x plus x square by 2, where x greater than or equal to 0. Noting that the derivative of log of 1 plus x is 1 by 1 plus x and derivative of x is 1 and derivative of x square by 2 is x, we obtain f prime of x is equal to 1 by 1 plus x minus 1 plus x, which is equal to x square by 1 plus x. The denominator is always positive and numerator is greater than 0 when x greater than 0. So we conclude that f prime of x greater than 0 when x greater than 0. Now what about f prime of 0? F prime of 0 is 1 by 1 plus 0 minus 1 plus 0. So which is 1 minus 1 is equal to 0. Therefore, f is a strictly increasing function for x greater than or equal to 0. Now x greater than 0 implies, noting the fact that f is a strictly increasing function for x greater than or equal to 0, that f of x greater than f of 0. What is f of 0? F of 0 is log of 1 plus 0 minus 0 plus 0, which gives log 1, which is 0. So we conclude that x greater than 0 implies f of x greater than 0. F of x is log of 1 plus x minus x plus x square by 2. So that is greater than 0 implies log of 1 plus x greater than x minus x square by 2 for x greater than 0. Similarly, by considering the function capital F of x is equal to x minus x square by 2 times 1 plus x minus log of 1 plus x, we can show that log of 1 plus x less than x minus x square by 2 times 1 plus x. Expressions 1 and 2 gives the desired result.